Euler's theorem on homogeneous function. Let's see what this is about. Let's look at this statement. If U is a homogeneous function of degree n in two variables x and y, then what happens? X times the partial derivative of u with respect to x plus y times the partial derivative of u with respect to y is equal to n times u. Alright? Now remember what the statement is saying, is this, the first part is that u is equal to f of x, y. U is the name of the function. Just like here had y equals something, this, that, and the other happened to x, and you say dy by dx. Now u is equal to something happened to x and y, so you say the u by dx with respect to x, and then I mean the delta u by delta x when you differentiate with respect to x, and then delta u by delta y when you differentiate with respect to y. Alright? Anyway, let's look at the proof. The proof of this statement. Now, here, let u be equal to, now it is, call this a1, which is a number, x to the alpha 1, y to the, we write beta 1, let's call it b1. Or instead of alpha, let me use lowercase a. X to the a1, y to the b1, plus a2, x to the a2, y to the b2, plus a3, x to the a3, y to the b3, plus, and so on and so forth, and the last one plus a n, whatever n is, x to the a n, y to the b n. You might be saying, what type of function is this, and so on. Well, this is somewhat like, if you remember, well, you should remember your binomial theorem. You remember that? Where you had something like nc0, or say ncn, x to the n, y to the 0, right, plus nc n minus 1, x to the n minus 1, y to the 1, plus nc n minus 2, x to the n minus 2, y to the 2, plus, and so on and so forth. It's somewhat like that, binomial, right? You might have a case where you have 7c 7, x to the 7, y to the 0, plus 7c 6, x to the 6, y to the 1, plus 7c 5, x to the 5, y to the 2, Right? It's somewhat like that. Now, here in the binomial, notice n plus 0 is n minus 1 plus 1 is n minus 2 plus 2 is n, and so on. Like 7 plus 0 is 7, 6 plus 1 is 7, 5 plus 2 is 7. So the powers, they add up to the same thing. Alright? And you have a number in front here. This number is like the A1, the uppercase A1, the uppercase A2, uppercase A3, right? And it so happens here too that the powers add up to the same thing. Alright, so let's get rid of this and continue. Now, A1 plus B1 is same as A2 plus B2, same as A3 plus B3, and so on. Alright, it's the same thing. So we have this type of function here. Now, when you look at all of this, it's n, the degree n. Alright? So remember, it's a homogeneous function of degree n. When you look at the variables, just as we did in the previous video, we add up all the x's and the y's. They are a1 x's and b1 y's. So when you add up the powers of the variables, they are equal to the degree, which in this case is n. Alright? Now, we want delta u by delta x. Suppose we differentiate this with respect to x. What would happen? Delta u by delta x would be equal to, well, we have this come down, the power, right? And we reduce that power by 1. So we have a1, big A1, then small a1, x to the a1 minus 1, and y to the b1. You see that? Alright, so we have that. Plus, then we have our a2 here. We differentiate with respect to x, you know. So the power rule, bring down the small a2, x to the a2 minus 1, b to the b2. Alright. Plus, same thing happens here. We have our a3, bring down our a3, x to the a3 minus 1, y to the b3, plus, and so on and so forth, plus, and the last one now, an, it's big an, uppercase an, or capital An, we have our common an, x to the an minus 1, y to the bn. Alright, so that's what we have for our delta u by delta x. But now, the thing is, we don't want any x to the a1 minus 1, and we don't want the minus 1s in the power. So what can we do? Well, whatever we're going to do, it happens that we're going to get the x times delta u by delta x. So what we want to do is go from delta u by delta x to x times delta u by delta x. So it's consistent with what we have up here. So what we do, multiply by x. So when we multiply by x, we have x times delta u by delta x is equal to, alright, if we do this, we're going to have a1 up capital A1 common a1, x to the a1 minus 1, y to the b1. Then we're going to have an x here, If we multiply this by x, this is x to the 1, right? And when we add the powers, a1 minus 1, remember, I don't want it to look this way. This is a subscript 1, right? It's not 1 minus 1, it's a1 minus 1 times x to the 1. When we multiply x to the a1 minus 1, x to the 1, laws of indices, we add the powers. So it's going to be the powers here. What is a1 minus 1 plus 1? This will go. So it's a1. So this will just be x to the power of a1. You see what happened there? Alright, we can draw the y to the b1 closer now. We use up the space. Alright. Now, here, we're going to have a capital A2 times common A2. Now, when we multiply this by x, the same thing would happen. It's going to be multiplied by x to the 1. And when we add the powers, we have a2 minus 1 plus the 1 from the new x. And the negative 1 plus 1 will go. So we have x to the a2 y to the b2 plus. When we do it here, we're going to have capital A3 common A3 x to the a, we're going to be x to the a3 minus 1 times x to the 1. But x to the 1, we add the powers, laws of indices, but negative 1 plus 1 is 0. So we end up only with x to the a3, just as before. Alright? So it's going to be x to the a3. Then we have our y to the b3 plus, and so on and so forth. Then plus, this is going to be a n, a capital an common an. Then x to the, well, we're going to have a n minus 1. When we multiply by the new x, is x to the 1. We add the powers by the laws of indices, but negative 1 plus 1, that's 0. So that is gone. And then we have y to the bn. You see that? That's what we have. Now, here, we are ready to do partial derivative of u with respect to y. By the way, let me just remove this part here. Let it look like u. Don't want the tail to be too long to start looking like y. Alright, what is delta u by delta y? We have delta u by delta y is equal to, we have our a1 x to the a1, so it's capital A1 x to the common a1. What will happen to the y part? We're going to have b1 coming down in front, and then reduce this power by 1, y to the b1 minus 1. So we're going, alright, it's too close now. Let me give it some space because I want the b1 right beside here. So it's b1 y to the b1 minus 1. You see that? Plus, alright, let me just write what we had originally. a2 x to the a2 y to the b2. We have a2 x to the a2 y to the b2 plus, but when we differentiate this b2, will come down here b2, and then we reduce the power here by 1, b2 minus 1. Alright, so this is b subscript 2 minus 1. Alright, so you see what happened there. And then plus, originally we had a3 x to the a3 y to the b3. So that's what we had. A capital A3 x to the common A3 y to the common B3. Then when you differentiate this B3 is going to come down. So you have B3. Alright. Remember, these are subscripts. Then we're going to minus 1 from the B3. So we have that. Plus. Alright. The last term, what happened here? an x to the an y to the bn. So we have an x to the an y to the bn. But when you differentiate that, oh my, why write it so close? Let me put some space. Alright. When you differentiate this with respect to y, bn will come down here, and this bn minus 1. So you see that. Then we want to go from from delta u by delta y to y times delta u by delta y. So when you multiply this by y times delta u by delta y is equal to a1 b1 x to the a1 y to the, if we multiply this by y, this is b1 minus 1 times y plus, we're going to fix it up after. Let's just put in the y for now. a2 b2 x to the a2 y to the b2 minus 1 times y plus. Then this is a3 b3 x to the a3 y to the b3 minus 1 times y plus, and so on and so forth, plus, and the last term is going to be an bn x to the an y to the bn minus 1 y. Now let's fix it up. Here y means y to the 1, and when you multiply y to a power times y to another power, you must add the powers, right? Remember your laws of indices. So if you do that, it's going to be plus 1, but negative 1 plus 1, that goes to 0, right? So this part is gone, and the same argument will apply to all the others. So this y to the 1, so this 1, that goes. This y is to the power of 1, so minus 1 plus 1, and that goes. And then finally, this y is to the power of 1, you add the powers, bn minus 1 plus 1, and that part goes. So this is what you have left. Alright. That is what you have there. Now, suppose you add these two things together. Remember what we had is x delta u by delta x plus y delta u by delta y. So we're going to say we have x delta u by delta x plus y delta u by delta y. Alright? What's going to happen? This is equal to, we have a1 x to the a1 y to the b1. We have a1 a1 x to the a1 y to the b1 plus. Alright, we're going to take this and add it to this. Alright, we're going to add these directly and see what happens. What we have is a1 b1 x to the a1 y to the b1. a1 b1 x to the a1 y to the b1. Alright, plus here this part here, a2 x to the a2 y to the b2, so it's a2 x to the a2 y to the b2 plus, that's up top, down the bottom here now, a2 b2 a to the a2 y to the b2, so we have a2 b2 x to the a2 y to the b2 plus. Alright, part with the trees, x that, this part with the tree, a3 x to the a3 y to the b3, so we're going to have a3 x to the a3 y to the b3 plus, and then the one with the y delta u by delta x with the three parts with the a3 b3 x to the a3 y to the b3, so it's a3 b3 x to the a3 y to the b3 plus, and so on and so forth plus, and then this last part now up here, an x to the an y to the bn, so it's an x to the an y to the bn plus, and then here we have an bn x to the an y to the bn, so it's an bn x to the an y to the bn. Alright, now here what's going to happen? You see this plus this, we have a common factor, you know? We have a set of common factors. a1 occurs in both, x to the a1 y to the b1, so let's factor that out. a1 that's not a common factor, it's a x to the a1 y to the b1, open bracket, then we have a1 plus b1. You see that common factor there? We factorize, right? And by the factors, a1 x to the a1 y to the b1, those are common factors, we factor those out, and then a1 plus b1 in bracket, alright? Plus, now let's examine this part. a2, the common factors are a2 x to the a2 y to the b2, so a2 x to the a2 y to the b2, inside the bracket we have a2 plus b2 plus. Alright, what happens out here? The common factors are a3 x to the a3 y to the b3. Alright, so it's a3 x to the a3 y to the b3, and we have brackets. Inside the bracket, what happened? a3 plus b3, so we have a3 plus b3 plus, and so on and so forth plus. Alright, common factor, we have an x to the an, y to the bn. So we have an, x to the an, y to the bn. What do we have inside the bracket? An plus bn. So inside the bracket we have an plus bn. Alright, so let's see what happens here now. This is equal to. Now, here, what we said earlier was a1 plus b1 is it equal to a2 plus b2 is equal to a3 plus b3 and so on is equal to an plus bn, and all of that is equal to n. So if that is so, then mean that a1 plus b1 is n. So you have a1 x to the a1 y to the b1 times n. Alright? Plus, so we have our n there. This is a2 x to the a2 y to the b2 times, this is n times n plus, here we have a3 x to the a3 y to the b3 n, because this is n, plus, on and down it goes, plus. And what happened here now? A n x to the a n y to the b n, and this is n. Alright. Now it is equal to, if we look here, we have a common factor known as n. So if we put n outside the bracket, inside the bracket we have a1 x to the a1 y to the b1 plus a2 x to the a2 y to the b2 plus, we have a3 x to the a3 y to the b3, 3 x to the a3 y to the b3 plus dot dot dot, it goes on, plus, and then it stops at a n x to the a n y to the b n. Alright. Now here, this a1 x to the a1 y to the b1 plus a2 x to the b2 y to the b2 and so on, what is it? It is u. This is a function that we had called u. So all of this part is u, so it is equal to n u. So therefore, what we have is that x delta u by delta x plus y delta u by delta y is equal to n u. So we prove Euler's theorem. Alright? So here we go. Prove